In this video, we're going to be going over chapter 3.7, Polynomial and Rational Inequalities. So due to the intermediate value theorem that we learned in a previous lesson, the values of the polynomial function p don't change sign between successive zeros. The graph of p is entirely above or below the x-axis between zeros. So we can see here that our red dots are like the zeros. So we can see that between zeros that are next to each other, our graph is either below the x-axis, like here, or between these two zeros, it's above the x-axis, and then between those two zeros, it's below the x-axis between successive zeros. So that's going to help us graph and analyze our polynomial inequalities. So a polynomial inequality is an inequality that can be put into one of the following forms. So I have f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0. So in solving polynomial inequalities, we have this procedure here. So we can express the inequality in the form f of x is less than 0, or f of x is greater than 0, and then we could have or equal to with these, where f is the polynomial function, and then we're going to solve the equation f of x equals 0, and so these real solutions are going to be our boundary points. So we're actually going to solve for our zeros, basically, when we set our numerator equal to 0, and we find our zeros. And then we're going to locate the boundary points or the zeros on the number line. And this is going to help us divide the number line into intervals. And then we're going to choose a representative number, which is called the test value within each interval, and evaluate f at that number. So if the value of f is positive, then f of x is greater than 0 for all numbers x in the interval. If the value of f is negative, then f of x is less than 0 for all numbers x in the interval. And then we're going to write the solution set, selecting the intervals that satisfied our given inequality using our table of test values. And then we're going to check if the endpoints of the interval satisfy the inequality. And then if we do, we would do brackets instead of parentheses to include the endpoint. Okay, so for example, we're going to solve 2x cubed plus x squared plus 6 is greater than or equal to 13x. So our first step is going to move all terms to one side. So we're going to add 13x. And then our next step is we're going to factor. So we did this in a previous video using the rational zeros theorem. So I'm just going to write those out. So I have x minus 2, 2x minus 1, and x plus 3 as our factored form. So we could see that we have zeros or boundary points at x equals negative 3, 1/2, and 2. And so we're going to break that up into intervals. So usually we do negative infinity to the lowest 0. So negative 3 is our least 0. So we have negative infinity to negative 3. Our next interval is going to be negative 3 to our next 0, or the next lowest 0, which is 1/2. And then I have 1/2 to the next 0 is 1/2 to 2. And then 2 to infinity is basically our greatest 0. And then if we go to infinity is the interval. So now we do our table. And we use our intervals. So we have like negative infinity over here and infinity over here. And we have our zeros, negative 3, 1/2, and 2. And so we break this up into our sine of x minus 2, sine of 2x minus 1, sine of x plus 3. And if we find the sine of each of those, basically, when we multiply the signs together, we get the sine of the whole thing kind of thing. So we take test values in between each interval and then plug them in to f here. So we have here we have our negatives and positives. We just want the signs. So the sign of x minus 2 times 2x minus 1 times x plus 3. A negative times a negative is positive. Positive times negative is negative. So we're negative for the interval negative infinity to negative 3. For negative 3 to 1/2, we have negative times a negative is a positive. Positive times positive is positive. So we're positive in this interval. The next interval, 1/2 to 2, we have a negative times a positive is negative. Negative times positive is also negative. So we're negative in that interval. From 2 to infinity, we're positive all the way down. So we're positive in that interval. So our inequality is that this is greater than or equal to 0. So we need positive values. So the inequalities that are satisfied, the inequality satisfied on the intervals negative 3 to 1/2 and 2 to infinity. And then when we plug in our endpoints, negative 3 and 2, to our factored polynomial, they are also, we're plugging in negative 3 here and then 2 and 1/2. They satisfy, they are greater than or equal to 0. So basically they're all equal to 0, but since our inequality is equal to 0, greater than or equal, they satisfy it. So our solution set is negative 3 1/2 union with 2 infinity, including those points. So I have our zeros here, and then I just connect them all. And I connect them knowing that between negative 3 and 1/2, we're greater than or equal to 0, which means we're above the x-axis. And then also from 2 to infinity, here, from this 0 up, we're greater than, and then everything else is going to be below the x-axis. Okay, so in our next example, we're going to solve and graph 2x squared plus x is greater than 15. So I have 2x squared plus x, and I move the 15 over, so I subtract 15. And then our next step is to factor. So I go ahead and factor it. Notice our coefficient of x squared is greater than 1, so our factoring is a little bit different. I get 2x minus 5 times x plus 3 equals 0. And then our zeros are x equals 5/2 and x equals negative 3. So use these zeros as our boundary points. So when I draw, this is kind of a different way than the first example to do intervals, but they both work, whichever one works for you kind of thing. I'm doing the examples in different ways to see which one you guys prefer for finding intervals and like doing your test values. But so when we have negative 3 here as our 0 and 5/2 as our 0, negative infinity is over here and infinity is here. So we're breaking out the real numbers basically. So this is our first interval, negative infinity, negative 3. Our next interval is negative 3 to 5/2, and then 5/2 to infinity is that interval. So now we make our table of values. So we have our different intervals, and then I put our test values here, which are between the intervals. I substitute into f of x equals 2x minus 5, x plus 3. So here, it's positive, negative, and then positive. So in conclusion, for negative infinity to negative 3, we have f of x is greater than 0 for x in that interval. For negative 3 to 5/2, we have f of x is less than 0 for x in that interval. And for 5/2 to infinity, we have f of x is greater than 0 for that interval. So therefore, the intervals that satisfy our inequality of being greater than 0 are negative infinity to negative 3 and 5/2 to infinity. So our solution set is negative infinity to negative 3 union with 5/2 infinity. And we see that the endpoints don't satisfy. These endpoints don't satisfy our inequality because when we plug them in, we get 0. But our inequality is just strictly greater than 0. So we have parentheses there. And for this example, I just graphed the, basically I graphed the inequality. But in this example, I'm graphing the solution set, basically. So I have -3, and then open parenthesis, or we could do an open dot, and then 5/2 to infinity. So that's our solution set. Okay, so now we're going to learn how to solve rational inequalities. So rational inequality is an inequality that can be put into one of the forms. F of x is less than 0, f of x is greater than 0, or equal to in both of those cases, where we have polynomials on top and bottom. So an example is like 3x plus 3 over 2x plus 4 is greater than 0. So the vertical asymptotes of the rational function break up the graph into separate branches, basically. So if our r of x equals p of x over q of x is a rational function, we have cut points of r, which are the values of x at which either p of x equals 0 or q of x equals 0. So in other words, our cut points of r are the zeros of the numerator and the denominator. So to solve, we use test points between successive cut points to determine the intervals that satisfy the inequality. So here's our steps of solving. So we move all of our terms to one side, and we get 0 on one side basically. We factor the numerator and the denominator, and then we find the cut points. We do that by setting the numerator and denominator equal to 0 and solving. Then we find the intervals determined by the cut points. So basically, by setting our numerator equal to 0, we're solving for the zeros. And then by setting our denominator equal to 0, that's solving for the vertical asymptote. So from here, it's the same as solving polynomial inequalities. We make our table, find out which ones satisfy the interval, and then we solve, and then see if the endpoints satisfy the inequality. So here we're going to solve and graph the solution set x plus 1 over x plus 3 is greater than or equal to 2. So our first step is we get 0 on one side and move 2 over. So I do minus 2. And then I'm going to combine them, the x plus 1 over x plus 3 minus 2, using the least common denominator. And I get negative x minus 5 over x plus 3 is greater than or equal to 0. So my cut points, or my x-intercept or vertical asymptote, I set the numerator and denominator equal to 0. So I get x equals negative 5 and x equals negative 3. So I find my intervals with those. So I just do it on the real number line. So my intervals are negative infinity to negative 5, negative 5 to negative 3, and negative 3 to infinity. So I set up my table. I have my test values of negative 6, negative 4, and 0. When I substitute them in, I get negative, positive, negative. So for the interval negative infinity to negative 5, I get f of x is less than 0 for that interval. For negative 5 to negative 3, I get f of x is greater than 0 for that interval. And then negative 3 to infinity, I get f of x is less than 0 for all x in that interval. So from our original equation, we're interested in solving f of x is greater than or equal to 0. So we know that f of x is greater than 0 for all x in negative 5 to negative 3, as the inequality involves greater than or equal to. So we have that, and then we have to include the solution to f of x equals 0. So we have to include negative 5 in this solution set, and it also satisfies our inequality when we plug it in. So we have negative 5 plus 1 over negative 5 plus 3 is greater than or equal to 2, which is true because we have negative 4 over negative 2, which is greater than or equal to 2. But then when I plug in negative 3, that's not true because we get 0 on the denominator. That's why we don't include the point 0. Or negative 3, sorry. So I have negative 5 to negative 3 is my solution set here. And I have a closed dot at negative 5 and an open dot at negative 3. Alright, so in my next example, I'm going to solve the inequality x squared minus 4x plus 3 over x squared minus 4x minus 5. So I factor it. I get x minus 3 times x minus 1 over x minus 5 times x plus 1. So my cut points are -1, 1, 3, and 5. So I split those up into these intervals here. And you can do that by doing the real number line or however you want them. Then I have my signs of my various factors, basically using the zeros and like writing them as like x minus 1, x plus 1 kind of thing. And then that gives us the overall sign when we're combining the different signs. And then I have each interval and I'm using test points between each. So here I have positive, negative, positive, negative, positive. I do my test points. And you could always do this way or the other table that I used in the other example, whichever you prefer. So we could see that our inequality is satisfied when it's greater than or equal to 0. So it's satisfied on the intervals, -infinity to -1, 1 to 3, and 5 to infinity. And then we check the endpoints. So I check 1, and that one works. And then I check 5, and that one does not work because we get a 0 on the bottom. And then when I check -1, that's the same thing. And then when I check 3, this one also satisfies it. So my solution set is -infinity to -1, unioned with 1, 3, including those points, unioned with 5 to infinity. And here I just graph basically my vertical asymptotes and then also my zeros. And that's how I get my graph. And we could do it by also like finding the horizontal asymptote, which we would see is here. So, okay. So here I'm just like graphing basically the whole graph, whereas like this is the solution set kind of graph. So here I'm not graphing the solution set, I'm just graphing the graph kind of thing. And you could do that like on by plugging in points and using our methods. So alright, so in this example we're going to do applications. So we have two light sources are 10 meters apart. The light intensity L in lux at point X in meters, from a weaker source is given by Lx equals 10 over x squared plus 30 over 10 minus x squared. So this is kind of I drew like a little picture here. They have a better one in the book. So we want to find the points where the light intensity is 4 lux or less. So essentially we need to solve 10 over x squared plus 30 over 10 minus x squared is less than or equal to 4. So we solve graphically by graphing y1 equals 10 over x squared plus 30 over 10 minus x squared, and y2 equals 4. So I just did this on Desmos using the 10 by 10 graphing window. So this is like the green is our y2 and the red is our y1. So in this problem, the possible x values are between 0 and 10 basically, because we have a distance is positive, and it's basically this whole line here is 10. And then this is x, and then this is 10 minus x there. So that's why I did it from 0 to 10 for our viewing rectangle, and we want to find the x values for which y1 is less than or equal to y2. So we see here that our our y values are less than y2 for all these right here. So the it's between 1.67 and 7.19. So our light intensity is less than or equal to 4 lux when the distance from the weaker source is between 1.67 meters and 7.19 meters. So And that's it for this video. So I'll see you next week in our following videos.